Linear program takes a lot of the ideas that we've been covering so far this semester and bundles them together into a problem where, unlike when we were solving systems of inequalities and we had an infinite number of solutions, we're going to narrow that solution down to one specific value that optimizes a specific expression. But we'll build our way up to that in pieces. The first thing that we want to talk about is this idea of optimizing an objective function. So in our problems, one of the things that we'll identify is an expression that we want to either maximize or minimize. In this case, we want to maximize the expression 5x minus 4y, meaning we want to find the xy pair that gives us the largest possible value for that expression that exists in a bounded feasible region. For these early problems, that bounded feasible region will be provided for us. Here we'll create it with the points 0, 0, 1, 9, 3, 7, and 6, 0. As we move on through these problems, we'll look at how we come up with these coordinate pairs and how we determine this objective function. For now, it's sort of just an arbitrary objective function just to demonstrate this process of how we're going to optimize this expression. What we'll do is plot these different points. In this case, 0, 0, 1, 9, 3, 7, and 6, 0. Once we have those points plotted, we're going to draw a polygon, so just a shape connected by all of those different points. And what we're going to be interested in are these different points or the corners of that bounded feasible region. Those are going to be our test points that we'll plug into the expression 5x minus 4y to see which one in this case gives us the maximized or largest function value. To do that in Desmos, we can click on the plus icon here and add a table. That table initially has 2 columns. We're going to click and add a third column, which will be our objective function. So in this case, 5 times x, but we're going to put a 1 after that, which will turn into a subscript 1, minus 4y1. That way what it's doing is referencing the x1 and y1 columns that were already created for us. In that x1 column, we're going to start off with our first x coordinate, which was 0, and then our second y coordinate, which is 0. And then we can press tab or click to keep moving through these different fields and enter our remaining values. So we had the coordinate pair 1, 9, 3, 7, and 6, 0. What we want to focus on is that third column. We're looking for the largest value, the maximized value that occurs from these different corner points. In this case, that largest value is 30, and that occurs when x is 6 and y is 0. So our optimal solution occurs at 6, 0, and that optimized function value is going to be 30. Similarly, in example 2, we want to optimize an objective function. The points that we're going to look at plotting here to create this feasible region are 0, 0, 4, 10, 5, 6, and 10, 0. Right now, don't worry about where those points come from. They're essentially just arbitrary at this point, just to create a feasible region. And what we're focusing on is just the idea that it's these corner points, those xy pairs that we want to plug into our function to see how we optimize it. In this case, though, notice that we're actually looking to minimize that expression. So our goal is going to be to find the smallest possible value when we plug in these different coordinates. Switching back to Desmos, we can create a new table. We'll add that third column, which in this case will be negative 2x2, since now we want to reference the x2 and the y2 columns in this table, plus y2. By clicking tab or just clicking into that next box, we can input our xy coordinate pairs. We're looking to minimize this expression. So in this case, that minimum value is negative 20, the smallest possible value we can get from these corner points, meaning our solution is going to be 10, 0, and that's going to yield that minimum value of negative 20. In both examples 1 and 2, we ended up identifying the point along the x-axis as our solution, but we don't want to get into the habit of kind of thinking that's a rule. Whenever we look at this, every one of these points is a possible candidate. We always have to test all of them and just see which one gives us either the largest, if we're looking to maximize, or the smallest value if we're looking to minimize that objective function.